Okay, so the worst feature of modern C++, default behavior. And if you have any questions to relate to the talk during, please just remember the slide, and the time for questions will be after. Unless this question, without the knowledge, you won't be able to comprehend the rest of the presentation, then scream, for example, banana and ask me a question. I will repeat a question to the microphone, so it will be recorded, and try to answer it as good as I can. Okay, so according to the plan, because there is a lot of weird behaviors of C++, and we have only an hour, I will be focusing on these 5 little features. Most of them were introduced in C++11, but some of them comes from older standards. And let's dive directly into first one. So auto, introduced in C++11, it is actually where the idea for this presentation comes from, because I used auto for the first time when I finally get my hand on C++11 compliant compiler, and after a while wrote something that more or less looks like this. So code is pretty straightforward. So we have a function that is, okay, this is visible, very good. We have a function that returns a reference to int. Then we have a function that relies on that function that returns a reference, and we have main when we use our modified int function and then strongly rely on the result of this. As if you are familiar with C++11 and auto, okay, the question I forgot to ask: how many C++ developers are there? Please raise your hand. Okay, so I have terrific audience. Very good. Okay, so you are probably spotted bug already. If not, let me show you a part of the standard. So you don't need to read all of them. In other words, this just means that auto uses template type deduction. If you are not, you don't know all template type deduction rules by heart, then this is the rule we are extremely interested in this case. So in its weird wording, it more or less says that auto does not deduce nor const or references or volatiles, whatever. So the bug is pretty simple to spot, but actually I didn't. All tutorials related to auto mentions it at the very beginning, but I am an engineer. I am supposed to write manuals, not read them. So after about half an hour of debugging, I learned the hard way, the thing that I supposed to read in manual. So the fix is pretty trivial. We just add a reference. And what have I learned? First of all, I learned that before the usage, always read at least 10 sentences from the manual related to this feature. Okay, this is quite a nice lesson. It's a shame that I learned it so late. The second one, auto, I already mentioned it, auto does not deduce these types. And I found this behavior a bit counterintuitive. Like, why new C++ feature that has no backward compatibility issues or whatever was designed a way that confused me, that worked against my intuition. And to cheer myself up, I just checked how many other people make that mistake at the beginning. So if you go through, there is a few pages of these questions, and the fun fact is that none of these questions was marked at Stack Overflow as duplicated. If you take a look even in the more details, you can see that there is a question directly from this year. So 6 years after introducing this standard, we still find this behavior quite counterintuitive. Okay, I'm cheered up. You know, we always have this after we are finishing a sprint, we didn't manage to deliver our part of the feature on time, so our assignment failed. But we know that our friend failed again, failed too. So yes, the blame is not only on us. No, the failed sprint is a detail. Okay, so I tried to find a good reason why it was defined that way. Actually, all of these questions on the Stack Overflow have great response with the reasoning, etc. But I'd like to propose another approach. Let's imagine, just for a while, that we are in the alternate universe when the auto worked according to my intuition. Maybe not yours, but mine. Okay, so a magical place when we have unicorns, pizza, and everyone is happy. So in each slide, there will be unicorn present. We are in this magical place where this expression is true, that auto, the variable of type, the type of variable A is a reference deduced from the return type of the function. Okay, so first of all, my initial code worked as it's supposed to be, as I assumed. So I have no topic for a presentation today, we can all go home. Except not a bit, because when we take a look to another example, when we are taking, we want to copy a pretty straightforward example. We have a pointer to an integer. We are assuming we are copying from that integer, and we modify a copy. And then we rely on this modification and that we didn't change initial value. So in this magical world, we won't get expected behavior because the return type of the star operator is a reference, because otherwise we would never be able to assign to it. So we are modifying in original object. We are not getting copy from it. Of course, it will be possible to do a copy using a static cast or not using auto or by introducing some other semantics to auto, but this is not something we want to do. So actually our unicorn looks more like this. And you know, this was a bit overcomplicated example. Actually, we got much straightforward example. So we have first auto variable I deduced to be an integer, but the second one will be deduced to reference in this alternate universe. So we can see that auto does not work at all. It's a bit useless. Excuse me, I need to catch a breath. Okay, so let's leave this twisted little word and get back to normal. So we can see that auto, the way auto was designed and the template type deduction rules are pretty well crafted that allows us to use auto far more intuitively than we made expected at the beginning. Okay, so as I said already, auto means template type deduction rule. Template type deduction, and this is quite nice rule to remember. But there is another feature with C++ because we cannot expect from the committee that they will assign only one meaning to the keyword. That will not be a C++. So we can another use case of auto. Pretty straightforward. This is alternate function syntax introduced in C++11, where we can specify a return type after the list of arguments, which is pretty useful, not in this example, but I will show where. So we learned that auto means template type deduction rules, except when it's not. Okay, let's go forward. Let's use this feature. This feature is useless in the example I showed you, but is very useful in case of templates. So we have a function that adds two separate types, and we want to deduce a return type from it because we don't know it before we know both arguments. Because we use a dec type over here, okay? We can use dec type over here to get a type of an expression is used, and use the expression that we type, for which type we want. And the reason why this dec type needs to go after arguments is because dec type use only on expressions, not on the types. Therefore, we need to know the type names before we use a dec type. Of course, we can write it without using this alternate function syntax, but we can all agree that this syntax is quite easier to write and read. Okay, so we have a new feature of auto. Let's use it. Okay, so let's say we want to write a function, a class that will be wrapper for a unique pointer. We want to add some extra behavior, like for example, checking for nullity at construction or reporting at destruction, whatever. Just a wrapper for the unique pointer. If you were on a presentation done by Mark Isaacson today, you will know that in C++, possibly 20, you will be able just to overload operator dot. But in this case, we just need to, we are still in C++ 14 or maybe 17, we need to implement full-blown object. So we take our unique pointer as a member, and we need to define operator star. And because we want to make our wrapper as thin as possible, we can just base on the return type of the operator star from our unique pointer. This is quite nice. We are robust for the changes of the unique pointer. So if committee ever decide to change the return type of operator star of unique pointer, we will not need to change our implementation. It will be aligned automatically. And okay, everything is fine, except there is one minor issue that most of C++, most of computer science engineers find quite disturbing. There is a code duplication. We need to repeat our expression from a return statement in the dec type. And we want to get rid of this code duplication. So all we need to do, because we are talking about C++ 11 standard, all we need to do is wait a 3 years and get a compiler compliant with C++ 14, where this arrow and dec type is optional, and we tell a compiler that we want a type deduced directly from the return statement. No code duplication anymore, hooray. Except we just introduced a bug. Because dec type extracts a type of the expression directly. So if expression returns a reference, the reference will be deduced. Same for const, same for volatiles. In case of auto, we have template type deduction rules, and we already learned hard way that auto does not deduce references. So we may fix it the same way we did it for the fixed example I shown, but we lose that nice feature that our implementation is 100% transparent for the return type of operator star in UPTR. So in case committee decide that unique pointer will return proxy object instead of actual reference to pointy, we need to adjust our implementation. So we have a fix for that introduced in C++ 14 also. We may tell compiler that we don't want to use auto template type deduction rules. We want to use rules used for dec type. And just if you don't know which set of rules pick, you have both keywords here, pick one. Okay, we talked a bit about auto. We already know what dec type does. I propose to start a quiz. I will show you a code snippet, and please shout at me what will be type of variable y. So what will be type deduced by, extracted by dec type. So first code snippet. Exactly, integer. This was a warm-up. Let's go forward. Very good. Reference to integer. Forward. Pretty good. You're better than I expected. Let's go forward. Yes, a double. Forward. Exactly, integer. Don't be so shy. I cannot spoil who gives the answer, so. Reference, exactly. Reference to an integer. Because operator star already said that returns a reference to an integer. Let's go forward. Okay, so I can throw out whole section. Okay, how about this one? Yes, it will be const reference to integer. I will explain why after. Okay, now. Yeah, pretty good. About how about now? Okay, array, what more? Okay, I heard a const char, I heard an array. There is one more thing missing. Yeah, array of const chars. Yeah, what more? Okay. Yeah, const char, array of const chars, and it will be a reference to this array because C does not allow us to create a copy of arrays directly. Okay, so you probably all are already familiar with that. Dec type has, I want to explain this additional params, why they cause a reference of the return the reference, not a direct type. So dec type has two different use cases. First of one is get the type of an entity, and second one is get a type of an expression. So when we look at the code, in the first example, we just getting a type of an entity, which will be int, as this is variable of type int. In second case, we just taking a type of an expression. This is pretty straightforward. By adding additional pair of params, we are telling to compiler that we don't want to get a type of an entity, we want to get type of an expression. So redundant params are redundant unless they are needed, actually. So in case of our structure, when we have a const pointer to a member, and by setting additional pair of params, we are telling to the compiler that we want a type of an expression. An expression will be always a reference type if we are referring to a variable with known name, but we have already a const pointer, so to retain const correctness of a program, we need to deduce also const here. Here we have, firstly, we are creating a variable of type const char pointer, because in template type deduction rules there is some weird thing called array to pointer decay to just keep compatibility with C, and then we just deduce this type. In case we are deducing from a string literal expression, this is actually a array of known type, of known size and known type to the compiler, and we cannot return via copy, we need a reference here. This is why we have such, let's say, complicated type returned by a compiler. Okay, enough of dec type. Let's get back to good old C++ 98, and at this point talk about default arguments. We have a pretty straightforward code snippet that sometimes yield quite unexpected behavior, at least for beginners. We have a function that just prints two arguments to ease an implementation. We have a class parent that will be used as our base class that implements single virtual function that takes an argument that we specify as default for equals 5, and all that function does is printing parent says and argument. In case of default arguments, it will be parent says 5. Okay, then virtual destructor, just to avoid memory leaks, and the class that inherits from our parent, let's call it child, and then override our virtual function. And all that function does is print child says and argument. In this case, we also want the default arguments to be a different one. In this case, equals 7. And just create a pointer to our child, assign it to the pointer for the base to have a virtual call, and call it. So what would be the output of this program? Okay, child says, because we all know how polymorphism works, but the child says 5. And actually, this was my face when I first saw that. Okay, so to fully understand why we get such output, so for those who don't remember, the 5 is a default argument for a base class. So to fully understand what happens here, we have to go through all phases that compiler has to do during calling a function. So first, compiler needs to perform name lookup. So it needs to find all the functions that matches actual signature of our function, actual name. Then if needed, we need to perform template type deduction if it found any template functions. Then we need to perform overload resolution, and there is a set of rules which overload should be picked in specific scenario. After overload resolution, we need to check if we found best function to call. We need to check if we have access to that function. So if the function is public or private or protected, and we have a right to call that function. And after these all steps, the virtual function call takes place. So at the very end, so we need to find where substitution of default arguments takes place, and this is actually needed for overload resolution. So far before we even bother about virtual functions. So in the great simplification, all the compiler does at this place, because it found function say in the base class, it just substitutes an arguments and get rid of default arguments in the declaration, just to make the work easier. And at this point, this is the mystery why compiler produces such weird output. Okay, so analyzing phases of the function call during leads to one more interesting finding. Actually, access control is done before virtual function call. So during calling a virtual function, compiler does not care of its access type. So we have a parent that is declared as struct. Therefore, our virtual function say is public by default, and child is defined as a class. Therefore, all the members are private defaultly, so our function say is private, and the proper function is called anyway. So this is small digression regarding classes. Okay, back to default arguments. We may create a function and specify its default arguments. And at this point, it will be function foo with single argument, with 2 arguments, and second one specified as with default value. Then we have a function main in which we call our function. So nothing magical happens. So in this case, we specify only 1 argument, second one is assigned with default value. But it turns out that in other scope than the one in our function is declared, we can redeclare default arguments and have this function called with different set of arguments. So in this example, we can redeclare argument b to be equals 7 and then call our function with single argument and have other default arguments assigned. We can even introduce new scope, redeclare both arguments and call our function with no argument. Why so? Because we can. We cannot use this declaration when we specify that we want a specific function code for the global scope, but we can still use the function declaration from a global scope. And just to be clear, the same implementation of the function foo will be used. And why is that happening? This is because in C++ standard there is a set of rules that specify when a certain declaration matches different functions, specifies different functions, and the default arguments are not in that list, so we can change default arguments or argument's name without changing the function we are referring to by declaration. So it turns out that we can create two declarations of the same function. In first declaration specify the last argument of our function, the next one specify the previous one, and this code actually compiles and works maybe not the way we expect, but it merges two declarations. So in this line we have a function call with first argument equals 5 and second argument equals p. Sorry. Okay, if you are more interested in C++ default arguments, there's a great talk from CPPCon from this year by Michael Price, where when he gives a full talk about the default arguments, and there is a lot of these weird scenarios in that presentation. Okay, we have 2 topics left, so there is a possibility that we will go home today earlier. So, R-value reference. Getting back to modern C++, actually, feature introduced again in C++ 11. Simple code snippet. We have 2 declarations of the function. One overload is for L-value reference, second overload is R-value reference, and all we do in this function is just report whether we have L-value or R-value. And then we create a variable which type is specified to be R-value reference, and then call a function. Whoever has experience with R-value reference, he already knows that this is not quite an output that someone can expect encountering R-value references for the first time. So the output is we got L-value. And again, weird face. So the usual explanation on this as a first sentence is that the variable of type R-value reference to type T is an L-value itself. So we are telling a newbie that R-value is an L-value. So something went wrong during the way of explanation. There is, again, a lot of great explanations all across the internet, but when we talk R-value is an L-value, we can expect that we are not understood correctly. So let's again imagine we are entering a special place where a code may behave according to the intuition. Where we create a variable of type R-value, always the proper overload will be called at this place. So again, a special place with unicorns and pizza, and same rule applies here. When there is a unicorn in the presentation, then there is a special place. So in this special place, when we call a function foo, actually the R-value reference overload will be called. And everyone is happy and feature works according to the intuition. Okay, so let's think about other example. We have a function foo that takes a string via copy, because, for example, we want to consume or modify this string during the runtime of that function. And we have a function bar that is overload for an R value reference. So we are taking the ownership over this object. So at this point, we are calling function foo, and because we are taking a string via copy in that function, the proper constructor is called, so constructor of string knows that we are passing R value reference, then we don't need this object anymore, and it steals its content. So actually, after calling this constructor, our variable in this scope is no longer useful, and when we want to use it again, we actually can't. Or in case of string, this is actually pretty well defined, because when we move from string, we get an empty string. But all standards requires is that the object from which we moved is properly destructible. That's all. We are not supposed to use our objects after moving from them. So we may face still in this magical place an undefined behavior. So again, this unicorn is not that pretty as we expected. So back to the normal world. We talked already about R value reference and what would be C++ without templates. So let's use C++ templates and C++ R value reference. So we may expect, if we have functions that have overload both for R value and L value, we may introduce the template code that we behave the same way and use the same syntax. So we specify the function for our template type, but L value for it, and our template type with R value for it. Except we can easily imagine if we have a template function that have more than one argument, and we want to handle all cases where some variables are R value and some variables are L value, we will need quadratic number of functions for the number of arguments. So for 2 arguments, we will have to define 4 overloads for a function. Therefore, C++ introduced a nice feature to avoid such code duplication. It is not called this way directly in the standard, but we used to call it forwarding reference. So every time we have a template type deduction and double ampersand, which looks like R value reference, we actually got forwarding reference. So instead of using std move for it, we are using std forward. Forward means that we either move it if it was R value reference, or we just pass it via L value reference if it's L value reference, if the type T is L value reference. So far so good. There is a small single detail that made this feature quite weird. We use the same syntax for 2 different, quite related, but still different use cases. So in this case, when we have a structure that is template okay, I cannot spell it, sorry. We have a structure that takes template, and we have a function for it that takes t_ref. We actually are not taking forwarding reference, but we are taking R value reference, because there is no template type deduction during calling that function. Because when we specify a type and its template argument, this is where the template instantiation takes place. So when we call a function bar, we just take the type of template argument. Type of arguments for function bar is already known for the compiler. Therefore, there is no template type deduction takes place, and there is no forwarding reference, just an R value reference. And this is actually a bug that even pretty experienced C++ developers does in their code. So whether the decision of making two separate use cases, a single use the same syntax, were good or not, it's not to us to choose, but actually this is C++, so what could we expect? That, you know, wait a second. What if we want to specify template function that binds only to R value reference? Okay. This is weird because when we have template type deduction, we have forwarding reference. So all we have to do is actually writing simple enable if. So easy peasy, just for every C++ developer, this comes quite natural. So we are using a feature called Swiny just to tell the compiler that we don't want to generate the function for L value reference. So if you pass our function bar or an L value reference, you will get pretty nasty compilation error, but after a few moments of reading, you will find out why is so. Okay, and we are going quite to the end. So the last thing I want to talk about is a syntax of C++. And there is a small bug I've done quite a while ago. I was actually writing a Rive wrapper for a timer. And I wanted my code to be compliant with C++ 98, so no brace initialization or other fancy features, just good old C++ 98 or 03 code. So I had two different constructors, one where I use default timer from a Linux, and second one when I used timer provided by user. And then I decided that I want to test my code. So I create a new instance of a timer, passed it to my implementation of timer as a constructor parameter, and then assumed that after destructor being called, I could observe some result. Like, for example, the number of get time from my timer called at least twice. Okay, but already you can predict that this is the not behavior that I faced, as this code is in the slide. So actually, first of all, are there any C developers here? Okay, quite a few. Who of you can tell me why the hell does it compiles and works? Okay, it actually took me a few days to find out why even compiler allows us to write such code. For those who didn't spot, on line 3 we have additional parens around x. And when I look at the code, I feel the same way when I look at this picture, you know? There has to be a reason for that. Not particularly good one, but at least some reason. So at that point, I found out why we have this syntax allowed. There is actually some abominations allowed in C++, like pointer to the function, that needs additional parens in the declaration just for making it work and be parsed correctly. And therefore, when we create a pointer to a function, we need to allow these parentheses. And as you can easily spot, the actual output of this program is a default constructor. So all I did is declare an object of the type foo with a name a. So if I ever will read warnings from the compiler, I would be used that I declared a variable a that I never used. Okay, so this is pretty much the end of the talk. Thank you very much, and now it's time for questions.
Hi. On the slide 53.
Okay, let's get back to there. 53. Okay.
Okay, and I don't remember. I'm sure that on line 4, you shouldn't specify a default value for parameter A.
You don't need to, because there will be used this parameter. So it will be merged, and the actual function call will be int equals 5 and A equals P. This is something that C allows.
Okay.
Who next would like to ask question? Anything? Okay. Okay, so thank you very much for your presentation. I can't remember when last time I had such great fun, so I think that you deserve a big applause.